Hi, everybody. Thank you so much for joining us for today's research seminar. Today, we have Professor Pedro Moreno-Sanchez from the IMDEA Software Institute, who will be presenting his work titled Blitz, Secure Multi-Hop Payments Without Two-Phase Commits. Before joining IMDEA in October of 2020, he held a postdoc position at the Technical University of Vienna. He has also held positions at Ripple Labs and IBM-Research Zurich. Pedro's main research interests are distributed ledgers, privacy-enhancing technologies, and applied cryptography. He holds a doctorate from Purdue University in computer science, as well as both a master's degree and a bachelor's degree from the University of Murcia. Thank you for joining us today, Pedro, and I'm going to let you take it from here.
Thanks a lot for the introduction. It's a pleasure for me to be here talking about one of our recent works, which is about Blitz. It's a secure multi-hop payments without two-phase commits. And I know that the name seems a bit cryptic, but hopefully at the end of the talk, you understand what we mean by that. Of course, I have not done this alone, so it's a work from the PhD student Lucas Amayer and my colleagues Aniket Kate and Mathieu Maffei. So if you are here only to watch the first 10 seconds of the talk, so what we are going to talk to you about is this new protocol called Blitz. As I said, it's a multi-hop payment paradigm, and it works for payment channel networks. And why you should care about it? Because it's one protocol that hopefully can convince you that it's more efficient than what we have today in the Lightning Network and payment channel networks in general. We can reduce the collateral, the amount of coins that you lock from a linear time and the number of users in the path to constant. The transaction sizes or the contract itself has a smaller size. And as I will show, it's also more secure, so not prone to some attacks that we have in the Lightning Network today. But to ensure that everybody's in the same page, let me give you a bit of background and motivation for the problem. I guess in this crowd, it's not a surprise that current cryptocurrencies have a scalability problem. So we can handle some tens of transactions or hundreds of transactions per second at most, but this is not what we would like. And the problem in a sense is like because the blockchain, this distributed ledger, has to record every single transaction that happens in the system. And every transaction has to be verified by the global consensus. So it means that everyone checks every single transaction that happened in the blockchain. So as I said, this ends up in a transaction rate that is around 10 transactions per second Bitcoin, and it's far away from what we have in other systems like Visa or MasterCard. So one idea that had happened was, what if we exchange transactions off the chain? So why do we really have to put everything on the blockchain? So let's change transaction off chain and use the blockchain only for disputes. And this is the basic idea behind what we call payment channels. So imagine that we have two users, a typical Alice and Bob, and they want to pay to each other. So instead of having every single transaction in the blockchain, what they can do is open a payment channel where it's a single transaction where the Alice will commit two coins and Bob will commit 8 coins in the example. And once this transaction is in the blockchain, these coins are in escrow and the payment channel is actually created. That means that now they have an off-chain state that distributes the coins as they have agreed before. So Alice has 2 coins and Bob has 8. And now the only thing that they need to do is exchange messages between themselves in a peer-to-peer manner, authenticated the manner that they agree on how to update the channel itself. So imagine that Alice wants to pay 2 extra coins to Bob. The only thing that she needs to do is to authenticate, actually sign a message that says, okay, from the scroll, Bob, you can get 4 coins, and the 6 coins are back to you. And the same, this can be repeated several times, so we can have several stages of this payment channel. In particular, we can have arbitrarily many payments until we reach with the final state, or state where the people don't want to, Alice and Bob in this case, don't want to pay to each other, but they want to close the channel. And this comes again with a simple blockchain transaction or Bitcoin transaction where they take the last state that they have agreed upon and put it on the blockchain itself. So basically, the take-home message is that with payment channels, we can have arbitrarily many payments, and we only need 2 transactions on the blockchain, one to open the channel and one to close it. Said like that, seems like a really magic solution, a really good solution. The limitation is that these payment channels allow only, or a single payment channel allows only Alice to pay to Bob and vice versa. What we would like to have in practice is that everybody can pay to everybody else. One naive way to do it is really to open a channel with everybody else. So Alice could open a channel with Bob, Carol, and Dave. But this is really infeasible because, as we have seen, the users have to lock coins into the channels. That means that Alice will have to lock coins for each of the channels that she wants to create. So instead, what they do is like each user creates a bunch of channels with their friends, and then we can connect them, creating a network. So creating a link, we can link channels to form what is called a payment channel network. And with that, we can allow to have a payment between any two users, having a multi-hop payment between the sender and the receiver, as long as they are connected through a path. One example of such a technology that is actually deployed in practice, and it's called the Lightning Network. And this is actually getting a lot of adoption. So, I mean, these numbers are getting, I think they're a couple of days old already, but there is around more than $100 million locked into this network. The number of nodes is growing. We have over 26,000 now. And also these nodes have around 70,000 channels between themselves. So it's a technology, as I said, that is actually being used. And the main core functionality is perform payments between two users that don't share a channel between each other, but they are connected through the path. Let me tell you what I mean by an example. So imagine that Alice wants to pay 5 coins to Dave via Bob and Carol. The first thing that they will do is that Dave will sample a random element, X, and send Alice the hash of that element, Y. And as many of you know, like given Y, it's computationally infeasible to get the value X itself. So Alice seeing Y cannot learn what is X. And using this cryptographic property, what we can do is that Alice establishes a contract with Bob, which is called hash time lock contract. This contract has two main clauses, or two simple clauses. So Bob can get the money, in this case, 5 coins, if he's able to, given the value Y, learn the value X itself. If that happens before a certain timeout, in this case 3T, then Bob can get the 5 coins. Otherwise, because Bob may never find such a value, after the timeout, 3T, Alice can get the money back. And of course, because at the beginning, when Bob receives the contract, doesn't know the solution yet, one thing that he can do is forward the same contract, or the contract with the same cryptographic condition to Carol, and Carol does the same to Dave itself. Now, and this is called the commit, so basically every user has committed to the payment from left to right using the hash time lock contract. Now, because Dave knows the solution to the riddle, so he knew the value X because he created at the beginning, he can redeem the smart contract by showing the value X to Carol itself. Now, Carol, knowing the value X, she knows that it's the same that she needs to show to Bob now to redeem the corresponding STLC, and so on in the whole path until it reaches the sender. And like that, we say that the payment has been successful. This is basically, in a high level, how the payments in Lightning Network works. But I want to go now through a couple of drawbacks or things that would be nice actually to improve upon. So as some of you might have noticed, the payment itself works similar to what we have two-phase commits in the databases. There is one round where everybody in the path commits to the payment from left to right. Now, when everybody has committed, then there is a second round to release the logs from right to left. So in a sense, we need 2 rounds of communications. And here by round, we really mean this sequential pairwise communication that happens from sender to receiver, or the other way around, from receiver to sender. As I said, there's one round for the lock, and a second round for the release itself. So one question that we have is that, okay, why two rounds? So can we have it more efficient? Can we have a single round protocol? We will see later the answer to that. Another aspect that you might have noticed here is that the time that the coins have to be locked is proportional to the number of hops that are in the middle. What I mean by that is, for example, the time that the coins have to be locked in this first smart contract between Alice and Bob is 3 times t, because there are 3 hops left in the path. And the time between Bob and Carol is only 2t, and Carol Dave is t. So this is what we call staged collateral time. So you can imagine the longer the path, the longer we have to have this time actually locked. Given that, the second question is, can we have, instead of staged collateral time, can we have constant time? Can we have a contract that locks the coins at constant time t? This is independent of the payment path itself, of the length of the path itself. So basically, this is the two main drawbacks I wanted to highlight from the Lightning Network, and this is the motivation for our work itself. So the Lightning Network is already a technology that is deployed and has good properties. One is its scalability. So I mentioned that we can perform way more payments than we can do only in the Bitcoin blockchain itself. It has balanced security, so we can prove actually that no user will lose coins themselves, and has some notion of privacy that I will be happy to talk about it after the talk if you have questions. However, there are, as I have presented, there are a couple of drawbacks that would be nice that we can actually improve. So one of them is this stage collateral time. And the problem is that it really decreases the network throughput. Imagine that for some reason the payment is not successful. The coins has to be locked this total amount of time until it can be released at each of the contracts and used for another payment. So all the time that the coins are locked are time that the user are using their opportunity to use these coins for other payment itself. It takes 2 rounds, which is not optimal. As I said, it will be good if we can have a single round protocol. And the smart contract that they are using is this hash-time block contract that require that the underlying blockchain, in this case Bitcoin, has the support for this contract. So the scripting language of the blockchain has to support the logic of this smart contract. In Bitcoin, it's not a problem because it's supported natively, but imagine that we want to run the Lightning Network over other cryptocurrencies like Monero, Ripple, or not. We will not be able to use it as it is today. We will need to have some other. So we have to add the support for SDLC. And another issue that I haven't discussed here, but again, happy to talk about it afterward, is that the Lightning Network is prone to what we call the Warhol attack. There's an attack where the adversary in the middle of the path can make the honest users in the middle to lock coins for a certain time and still get the fees from the honest users itself. The details are in the paper printed here. I'm happy to talk it afterwards. So given that, this is what, as I said, what motivated us to think of a new construction for payments, for multi-hop payments. And the first attempt is that, okay, we want to have a multi-hop payment that works in 1 round. So what happens if we do it a straightforward manner? Like Alice really pays Bob without any condition. Bob forwards the money to Carol without condition again, and Carol forwards it to them. And this approach is used in some protocols. One of them is the interledger payments. However, as you might have noticed already, this protocol is prone to attacks where the intermediaries are not honest. Particularly, imagine that Bob is malicious. He could receive the coins from Alice, just run away or decide not to forward it to Carol itself. Therefore, we need something else if we want to have security against malicious intermediaries. Towards solving this problem, we define what we call the pay-or-revoke. This is a change in the payment paradigm, in the sense that now we don't have this two-phase commit, this commit and release, but what we do is the following contract. At each of the hops, let's say Alice to Bob, Alice will pay to Bob, but only after time t. And before that, she will have the capability to refund herself. So Alice will say, for example, in practice would be Alice, does Bob, look, I will pay to you tomorrow if the payment is successful. Otherwise, in the middle of the day, I can refund myself. Now, Bob does the same. So he forwards Carol these 5 coins with the same condition. And at the end, Carol forwards the payment to Dave on the same condition. And this moment, Dave knows that if nobody refunds after the time t, the day in the example I was saying before, Dave can claim the coins from Carol without any condition. Carol can claim it with Bob, and Bob can claim it from Alice. However, as you can imagine, this is not yet super secure. We have to be careful actually with this paradigm yet, because what the difference between the time where you can refund and the time that the payment gets actually valid is critical. So intermediary user like Bob could actually wait like a little time before T, get the payment from Alice, and at the same time try to refund from Carol. And if that happens, the rest of the users of the path don't have enough time to react to refund themselves from their payment. So what we need to make sure in a sense is that if some user refunds in the path, then everybody has time to refund and everybody can refund. In other words, the refund has to be atomic. And this is what we do in Blitz. This is what we call the final pay-or-revoke paradigm. So the trick here, the main technical addition is that Alice defines the timeout T, as we have seen before. And this timeout T is independent of the length of the path itself. Apart from that, Alice will create a transaction that we call TXER. So it's a refund transaction. And she will create, in this transaction, she will create an output with a small amount that we call here epsilon. And this epsilon, you can think of it as a small amount, like the dust or some hundreds of satoshis, for example. And the idea is that each of these outputs will belong to each of the users in the path. And we will see now why this is interesting or why this is useful. So as before, we will have Alice with the same contract. So Alice will pay Bob 5 coins after T, and will refund, can refund before T. But now the additional condition is that she can refund only if TXER has been published. So if TXER has been published on the blockchain. Bob will do the same. So Bob will forward the TXER to Carol, will forward the payment after T, and make sure that the payment can be refunded only dependent on TXER itself. And Carol does the same. I don't have the time to go through all the details of why this protocol works, but the intuition is that, okay, I forgot one step. Of course, at the end, when Dave gets a payment, has to send the coordination transaction to Alice for Alice to check that nobody changed it in the middle. So it's really crucial that everybody sees the same transaction. So to give you an intuition why this new paradigm would work, again, there are more details and a detailed explanation in the paper, that imagine first a successful payment. So like everybody really forwards the payment and nobody tries to revoke it. This is exactly the same case as before. So after time T, the payment gets successful, so they can actually establish this new state on the channel and everybody will get the 5 coins from the previous user in the path. Now the perhaps more challenging case is when there is a refund. Imagine that one of the users decide to refund the payment before time T. The only possibility that this user can do it is that if Alice has previously published this TXER. And if Alice has done that, that means that all the refunds of all users have been established before. So if we make sure that Alice published the TXER enough time before T, this will atomically allow all the refunds of all the channels in the path itself. So basically this transaction and this, or the structure of this transaction and the fact that it has an output enabling each of the refunds of the path is what makes the refund part of the payment atomic. Here I have shown only a couple of details of the protocol itself, but of course in the paper we have more details. So one of the aspects that we were asked a couple of times is that, okay, Pedro, you have shown a protocol where the money goes from Alice to Bob, is committed, but it's only get valid or established after time T. So which in practice will be some hours or 1 day or something along these lines. So what if the receiver really wants the money right now? So what if he needs it in the next minute or in the next seconds? So what we have that in the paper is what we call a fast track. It's like an extension of the protocol where we can really make the payment successful. Or after the payment is successful, we can make it immediate effective. And for that, we have the observation that once the contract has been established at each of the hops, is in the incentive to actually accept it and go to a next state of the payment channel where they have accepted the payment itself. And if we do it in the order from left to right, because Alice is the only one that can publish TXER. So if Alice goes to the next state where it revokes TXER, everybody knows that TXER will not be published, the refund cannot be done, so the payment will be accepted. So with that, they can just go to the next state and simply accept the payment itself. As I said, bottom line, there is a way to make the payment faster and make it actually as instant as in the Lightning Network. There is also a way, similar with the similar explanation, there is also a way to make the revoke itself fast as well, really not to wait until Alice posts the TXER. So we can really make because everybody knows that the refund will be atomic once the TXCR is public. If they collaborate to each other, they can actually do the refund without the need to publish the TXCR to start with. And finally, you may have wondered that, okay, if there is a transaction that has an output to each of the users, means like there is a public key associated to each of the users, it will be easy to learn who is paying to whom, right? So if you have a TXCR, you will have a description there in that transaction about who are all the intermediaries in the path. So we solve that by, instead of having the public keys, we use the mechanism of staff addresses, similar to how it's used in Monero, to hide the actual identities of the intermediaries of the path. As I said, there are more details about how all these cases work in the paper, so I really encourage you to go there and check the details out. Finally, I would like to go through with some evaluation and comparison with the current solutions that we have. As I mentioned, one of the protocols that's actually implemented is this interledger payment, or ILP, where, as we have seen, when there are intermediaries that are dishonest, there is no balance security. They can run away with the money of somebody else. However, this problem is not in the other solutions that we have, like Lightning, AMHL, or Blitz itself. ILP is actually a solution where you have only one round of the protocol works in one round, while Lightning on AMHL works in 2 rounds. And Blitz is the only one that has a single round of communication, and it still has security. We still manage to ensure the balance security to all the users. We also, as we have seen, because there is only a single T, so there is only a single amount of time where each of the hops need to lock their coins. We have collateral lock time, which is constant in the path and doesn't depend on the number of intermediaries, as it happened with the Lightning and the AMHL, as I have shown to you before. Finally, also the atomicity means atomicity is another property that we're interested on. That means that either all the channels happen, or the payment happens at all the channels, or the payment is refunded at all the channels at the same time, or none of them happen. So this is not actually happening in the LP, not also in Lightning, because of the Warhol attack. And because of the user TXCR, we achieve it in Blitz, and AMHL also has this property. And finally, one feature that we find interesting in practice is what is the amount of logic or functionality that we require from the underlying scripting itself. For example, in the LP, we'll be able to work over any blockchain that only requires the transaction authorized by signatures. So if the blockchain, or the script of the blockchain supports smart contracts that are only based on digital signatures, one can deploy LP at the cost of having all the other drawbacks. In Lightning, it can work over blockchains that has smart contract support for signatures, time blocks, and hash locks themselves. So we need this hash time block contracts, basically. And in MHL and Blitz, we have seen that what we need from the blockchain below is only that transactions are authorized based on digital signatures, which is basically the vast majority of blockchains, and also has this concept of time lock, like coins are locked for a certain time and can be unlocked after that time itself, which is also another feature that is appearing, or is actually available in most of the blockchains, if not all today. We basically, Lucas managed to do run evaluation of the system itself, and we were curious about a couple of aspects in practice. So one of them was the size of the contract that is needed at each of the hops in the path. And what we showed is that the Blitz contract, the one that we need to encode this logic of pay after T or refund before T, it's 26% smaller than what we need in Lightning contract. This is 26% smaller than the ACLC. And this is important because we can actually use it to increase the number of concurrent payments in each of the channels. The reason behind, without going into many details, is that in every state that we have in a payment channel, let's say in Lightning first, we will have 2 balances, the one that has Alice and the other one of Bob, which are unconditional, the one that they can always get. And then a copy of each of the smart contracts for each of the payments that are still in flight. Means that they are being routed and they have not been released yet. And the important point is that the size of this transaction has to be within the size of one Bitcoin block, because this has to be in a single transaction and has to be possible to put it on the blockchain to close the channel. So this state can never grow more than the size of one block of the transaction limit that we have in Bitcoin. So in other words, the smaller is the size of the STLC or the smart contract for the multi-hop payments, the more in-flight or concurrent payments we can put within the state itself. Since here, because the Blitz contract is smaller, we can actually add more of those concurrent contracts. And in particular, we are actually allowing way more concurrent payments per channel than the Lightning Network. In order to show what is the impact of that in the Lightning Network, we took a snapshot of the current Lightning Network. And because we don't know exactly which payments are actually being used or who is paying to whom, because this is private information, we just conducted some payments at random. Some of what we decided are being disrupted, or they go through nodes that we consider malicious. And we studied what is the impact of having constant collateral, like the single T time T over the whole path, against having something like a stage collateral as we have in Lightning. And the result is that depending on the setting, what I mean is like depending on the structure of the graph, or how what type of random payments we use, or how the path, the length of the path that the payments use. So depending on the different settings that we used, there is an improvement with Blitz between 4x and 33x. In other words, like 4x or 33x fewer payments failed in Blitz when compared to the Lightning Network itself. As I said, in the paper, we also describe each of the settings and what are the differences in the implementation itself. So to conclude this talk, I have talked to you, and I hope I have convinced you that we have a new multi-hop, so Blitz is a new multi-hop payment paradigm for payment channel networks like the Lightning Network. We have managed to have a protocol that has a single round of communication, different to Lightning Network that has two, and still we don't give up on the security and privacies that the Lightning Network has. In fact, we actually improve them. What I mean by that is that we reduce the collateral from linear in the number of users in the path to constant. And we have a protocol that is secure against the walk-home attack, which is an attack that is possible in the Lightning Network today. Also, we have seen that from the practical point of view, we require only signatures and time blocks, which allows them to deploy Blitz over more blockchains, or blockchains that support smart contract support for only these two functionalities. And we have also seen that a detail, like a little peek of the evaluation that we have, and the paper there are more details about the simulation that shows the practical advantage of having constant collateral Blitz. Not only like a solution or a theoretical result, we show that having this constant collateral has a huge impact in practice itself. From the theory part, we have modeled the whole system in the universal composability framework, and we have proven that it has the security and the privacy guarantees that we expect. And the last point, which I wanted to discuss, is also that it's compatible with the Lightning Network, in the sense that we could have the Lightning channels as they are today, and have them implement the Blitz on top as a multi-hop payment itself. Of course, we have another work that is called Generalized Bitcoin Compatible Channels that improves upon the behavior of the single payment channel itself. So having this other approach that is more efficient than the Lightning channels would also make Blitz more efficient and easier to integrate. But if not, we can actually integrate Blitz on top of the Lightning Network as it is today. And with that, I would just like to thank you for your attention, and again for the invitation. As I said, the paper is available in this link. I'm also available for questions now, and if not later, please feel free to reach me either by email or by Twitter. So thanks a lot.
Thank you, Pedro, for the presentation. Thank you so much, everyone, for joining us today. Really appreciate it. Remember, if you want to keep up to date with future talks and other developments here at Protocol Labs, make sure to sign up for our newsletters in the video description below. Also, make sure to take a look at our grants website. titled grants.protocol.ai for a list of open grant applications that we have to fund other future research that you may be interested in. Wanted to thank you again one last time for coming today, and we look forward to seeing you again soon. Bye.